Hello everyone. We'll be starting the class soon. I'm just waiting for a couple of minutes to see if anyone is joining. Meanwhile, I'll just set up the study notes. Okay. Hello everyone. Yeah, so we'll first look into the previous week what we have done, and then we'll continue with this week's studies. So last week we started with the absorption reaction. So resistance. So now we'll look into so this is the reaction. So let us first look into reaction. So what is it happening? So reaction. Solution is solution is there is an electron absorption reaction happening, which is this reaction where you have some impurities in the solution which is getting absorbed on the electrode surface and thereby blocking the effective area available for the reaction to progress. So this is the electron absorption reaction. So when large overpotential is applied, the forward reaction is happening, and this also means that the surface coverage of the air absorption, as in this reaction, will be increasing. So up to some potential, when O potential is increasing, we are catalyzing P giving Q reaction. But when it becomes excess, it also translates a forward reaction of the A adsorbed becoming what is it? A solution becoming A adsorbed. So that also gets catalyzed, and that will get adsorbed on the surface of the electrode and thereby reduce the effective area for catalyzing P giving Q. So after some point, when the potential is increasing, you see that the current decreases. So if no intermediate like that were available, that is the second equation is like second, that is the impurities are not available, then that reaction is similar to Fe2 plus Uv, Fe3 plus the first reaction we saw. That is the ferroferricyanide. So we first looked into how we write the rate of the reaction where R1 equal to K1 into P solution. But because the entire surface area is not available, let's say A adsorbed occupy theta surface. So because of that, we'll write the rest of the surface is equal is available for both adsorption of P solution or the A solution minus, which is a backward reaction. So in both reaction, R1 and R2 will multiply the reaction rate by 1 minus theta. And R2 becomes R minus 2 becomes K minus 2 theta. When mass balance is considered, which accounts for the fraction of site which is occupied by theta. So for that, we will not consider the first reaction but the other two. So R2 minus R minus 2, we are writing the expression. And then when we are equating the steady state, we are equating it to 0, that is steady state mass balance, we get the theta value. Then finally we get current density, which is NF into R1 plus R2 minus R minus 2. Okay. In that we consider all the reactions which is involving electron transfer. So all the three reactions have the electron transfer, so we are considering all of them. Then we write IF. Just give me a moment. So IF we wrote. Then we have to now, how is it different? We are considering the P solution, A solution. Theta is equal to theta SS plus theta dash EAC. Theta dash plus EAC. Then K1 equal to K1 DC into 1 plus B1 EAC. and K2 equal to K2 DC into 1 plus B2 EAC. K minus 2 is equal to K minus 2 DC into 1 minus 2 B minus 2 EAC. Now after that we are writing again, we are substituting the value of theta as theta SS plus theta dash EAC. We are then elaborating the rate constant in terms of the EAC applied. We will then subtract all the what to say. Just give me a moment again. Constants. We are already getting rid of the constant terms. We're getting rid of those terms when EC square comes, because when EC itself is small, EC square is also getting small value. So we are also neglecting those values. Then we will substitute and simplify it. We'll have to find out the theta dash value. So gamma dou theta by dou t equal to, the equation is there. Substitute, find out theta dash value. Okay, and when you have backward and forward reaction, we know the rate of forward and backward reaction becomes equal, and then we find a simplified substitution and we substitute back into equation. Finally, we get YF equal to IFAC by EAC equal to something like this, where theta dash value is also given over here. Now, this is what I was talking, up to some potential. When we are increasing the over potential, IDC keeps on increasing, after that it decreases. Then we also, something important that we saw over here was, what is RP and RCT? RCT is when omega tends to infinity. How do you simplify it? That is omega tends to infinity, so that entire term becomes 0, theta dash 0. This is the important thing for EEAM mechanism. This is how it comes. And similarly, when RP is a, you have to find a theta dash, then find a YF, set up to 1 by YF equal to RP. So this is what we did. We did few more questions. Yes, and we stopped it. Then I told you have to look into the three-step reaction involved in two adsorbed intermediate. Okay, so that's what I'll be starting with. And then we have to also look at the next topic. Just give me a moment. Then you have catalytic mechanism that you have to look at. Okay. So probably in this today's class, I'll be looking into the mechanisms mostly and discussing the assignment for the next class. Okay, because there is a lot of Trump isotherm is also coming in this chapter, so it will take some time to show the derivation. So this is what I've planned for today. And I think we haven't discussed few questions from the previous assignments. It's also I'll be discussing today. Okay. So till now, whatever the reactions we looked at, it was having only a single adsorbed intermediate. Now, how will it go if we have more than one adsorbed intermediate? That's what we're going to look at. So let me write the reaction. So there is a metal surface. The first step involves formation of one adsorbed intermediate, M adsorbed plus. In the second step, M adsorbed plus is consumed. It forms M adsorbed 2 plus electron. This involves consumption of the first adsorbed intermediate and the formation of second electrochemical intermediate. So in the second step, n adsorbed 2 plus when rate constant is K3, it becomes, it's going to solution as N solution 3 plus electron. So if you see the first step, formation of M adsorbed plus, second step, you have the formation of M adsorbed 2 plus and consumption of M adsorbed plus. Similarly, the formed M adsorbed 2 plus, it gets consumed in the third step. So here there are two adsorbed intermediates which are found, M adsorbed plus and M adsorbed 2 plus. Let the fraction of sites which are occupied by M adsorbed plus, will give them as theta 1, which is the fraction of sites occupied by M adsorbed plus. And for the fraction of sites which are occupied by M adsorbed 2 plus, will give it as theta 2. So if theta 1 is adsorbed, theta 1 is occupies is occupied by M adsorbed plus and theta 2 is that occupied by M adsorbed 2. What is the free metal surface available? It is nothing but, so if I say the total metal surface is 1, of which fraction, I mean 100%, this will be the fraction which is occupied by the free metal surface. Because the rest is adsorbed by M adsorbed plus and M adsorbed 2 plus. Now, how do you proceed with this problem? So, in this question, so method remain the same, where you write the mass balance, then you say steady state mass balance where you get theta 1 SS and theta 2 SS. Then after that, you will write IF formula from which you will get both IF DC and IF AC. IF AC is what is important for us. Then you will have theta dash. So differences here, mass balance input d theta 1 by dt and d theta 2 by dt will come. So when you are differentiating, you have both the terms involved. Okay. Then you will get through here theta 1 SS and theta 2 SS. You get IF, find out IF AC, IF DC. So when you're writing IF AC in terms of what? You will have to find out K1 DC, K2 DC and everything. K3 DC also. Find out the K values. You expand it. Then you will also have to expand theta 1, theta 2, theta 3. Then after that, you will have to find out theta 1 dash, theta 2 dash, theta 3 dash. Finally, you will have the ZF equation. So, the steps remain the same, but the only thing is the number of steps involved will be increasing. Okay. Same good. I know it's solving it fully, but I think we have a clear ideas on how to do this. So let's start by writing the mass balance equation. So, yeah. So all the steps are analytical steps. So we need to consider all the steps when writing the IF equation also. In this writing exercise, we will basically need to use it to analyze. Okay. So let's start this. So theta d theta equal to dt is equal to first we get the steps and answer and it's of plus. Which are the steps? The first step is there, second step is there. Third step, it is not there. First step involves formation of M adsorbed plus. So it is K1, 1 minus theta 1 minus theta 2. Second step involves consumption. So it becomes K2 mx of, sorry, K2 theta 1. Right? Now the next one, gamma d theta 2 by dt. Let's look into the steps which involves the formation and consumption of theta 2. So first step doesn't have m absorbed involved, 2 plus involved, so I'll be neglecting that step. But second step involves formation of m absorbed 2 plus, this is consumed, and the next step involves consumption of m absorbed 2 plus. So this one will also be consumed, sorry, considered. So now when I'm writing this, for second step involves, that is MH1 plus gives MH2 plus electron, involves formation of MH2 plus. So I'm considering that K2 into MH plus, so that is theta 1 minus, next step minus because it is getting consumed in the next step, K3 into theta 2. So these are the expressions you get. Now let us, so first step is done, that is to write the mass balance. Now what is the next step? To write the steady state equation. So if you see, let me go with the second equation first because this looks less complex. So I can get something in terms of another. So steady state, so it is in terms of dc, theta 1 SS equal minus K3 dc into theta 2 SS. What does first equation becomes? K1 dc 1 minus theta 1 SS minus theta 2 SS is minus K2 dc theta 1 SS equal to 0. Now, from this expression, I can say K2 dc theta 1 SS equal to K3 dc theta 2 SS. Right? Now, let's see if I can simplify it somehow. K1 dc. So, the simplification, so here what I'm going to do is, I'm going to open the bracket first, K1 dc, and take all the terms with theta 1 SS to the other side. K1 dc theta 1 SS plus K1 dc theta 2 SS plus K2 dc theta 1 SS. This is theta 2 SS. So if I have to find theta 1 SS, I have to substitute it for theta 2 SS somewhere. So we already know from this equation. I can write it for theta 2 SS. How can I write it? So from this equation, I know K2 dc theta 1 SS equal to K3 dc into theta 2 SS. I am taking K3 dc here equal to theta 2 SS. Okay. So this substitution goes over here. Becomes K1 dc theta 1 SS plus K1 dc K2 dc K3 dc theta 1 SS plus K2 dc theta 1 SS. Now what I'm going to do is I'm gonna take out K1 dc from all the expressions. What will I get? So K1 dc equal to K1 dc theta 1 SS into K1 dc. I'm taking out from all the expressions. This is simplification. You can leave it here also, but to have it in a neater form, we are doing this. K1 dc into theta 1 SS is taken out from this. This becomes 1. Same way, K1 dc theta 1 SS taken out. So what do you have? K2 DC, K3 DC. Next expression, we have K2 DC into theta 1 SS. So this theta 1 SS in this. Yeah. So if I take up K1 DC, theta 1 SS I have, but K1 DC is not there. So how will it be? It will be simply K2 DC divided by K1 DC, right? K1 DC and K1 DC goes. So you have 1 by 1 plus K2 DC by K3 DC plus K2 DC by K1 DC equal to theta 1 SS. This is the expression for theta 1 SS. Now you already know theta 1 SS into K2 DC by K3 DC equal to theta 2 SS. K2 DC by K3 DC. So that is same as writing 1 by, just taking a reciprocal here. So it becomes K3 DC by K2 DC. Right, the same as writing K2 DC by K3 DC. Just taking this down beneath K3 DC. And what is theta 1 SS? 1 by 1 plus K2 DC, K3 DC plus K2 DC, K1 DC. Now we are simply opening the bracket. We'll get because K2 DC is over here and here, I can simply take K2 DC inside. Let K3 DC be there. So it becomes 1 by K2 DC plus 1 by K3 DC plus 1 by K1 DC. So then the expression you will get for theta 2 SS. Now what is the next step? Next step is to write IF. So let's write IF DC first. So IF DC. Which are the steps? You have 3 steps involved and all 3 steps have electron transfer. So it's all the forward reaction. So you'll have to simply say NF into R1 plus R2 plus R3. Only if backward reaction is there, we will be taking negative. N value is 1. So you have 1 F into, what is R1? R1 is K1 into 1 minus theta 1 minus theta 2. What is R2? K2 into theta 1. Next is K3 into theta 2. Don't forget this all in steady state. So K1 DC 1 minus theta 1 SS minus theta 2 SS. K2 DC theta 1 SS. K3 DC theta 2 SS. So this is how IF DC will be covered. Now let us write IF. So when you get IF and you subtract IF DC from that, you will get IF AC. So this F into K1 1 minus theta 1 minus theta 2 plus K2 theta 1 plus K3 theta 2. Now what we have to do? We have to substitute to K1, theta 1, theta 2, everything. Yeah. So let's start doing F into K1 DC So before that, let's write down what is K1. K1 equal to K1 DC into 1 plus V1 EAC, right? K2 equal to K2 DC 1 plus V2 EAC. K3 equal to K3 DC 1 plus V3 EAC. Now what is theta 1? Theta 1 equal to theta 1 SS plus theta 1 dash EAC. Theta 2 equal to theta 2 SS plus theta 2 dash EAC. Theta 3 is theta 3 SS plus theta 3 dash EAC. So this is like the formula you have to learn by heart. K for any value ki, it becomes ki dc into 1 plus vi EAC. For anything it becomes. Now same with theta I equal to theta ISS plus theta I dash plus EAC. So derivation we have already looked at in the first mechanism we have seen. So this kind of by heart you need to know, and you will be substituting this and solving it. So let's do the solving. I'm substituting. Okay. Please let me know if you have any doubt in what I'm doing. So this is the full equation. Now we have to, I'll simplify it and then leave it over there. Then you will have to solve it. Okay. So yeah. No. So first I'll try to get the constants together. So I'm multiplying K1 DC into 1 to 1 minus theta 1 SS minus theta 2 SS minus theta 3 SS. Now next term becomes the same K1 DC when I'm multiplying it into 1 into these terms which I have not considered, which are they? Minus theta 1 dash EAC minus theta 2 dash EAC minus theta 3 dash EAC. Okay, now let me multiply K1 DC into B1 into EAC. I'm again multiplying with the constants here. 1 minus theta 1 SS minus theta 2 SS minus theta 3 SS. What about the next term? K1 DC into B1 EAC into 1 minus theta 1 dash EAC minus theta 2 dash EAC minus theta 3 dash EAC. Will that happen? No. I mean, it will happen. Do I need to consider that term in the question? The answer is no. Why? Because you will have EAC square in that. EAC itself is small value. When you're squaring it, it is even going to be more smaller value. So we can ignore that term. It will be closer to 0. So we don't have to consider that. Now let's look at the next one. K2 DC into 1 into theta 1 SS. So that's the first term. Then again K2 DC into 1 into theta 1 dash EAC. Now the next term becomes K2 DC B2 theta 1 SS EAC. Now, do I need to consider the next term, which is K2 DC into B2 EAC into theta 1 dash EAC? No. Why? You already will get 2 like EAC square. As mentioned, you don't need to consider because that will be very small value. Now, next term is K3 DC theta 3 SS K3 DC theta 3 dash EAC plus K3 DC B3 EAC theta 3 SS. Now let's ignore all the terms where only constants are there. You don't need them. Yeah. So which all terms need to be ignored? The first term, which is 1 minus theta 1 SS minus theta 2 SS minus theta 3 SS can be ignored. You're going to consider only those terms where you have EAC in those terms. The next term stays. The next term again stays because you have K1 DC B1 into EAC. Next term K2 DC into theta 1 SS? No. Whatever the next term K2 DC into theta 1 dash EAC? Yes, you have EAC in that. Next again, the next term is also considered. The next term is again left. Now, let us rearrange it. Like those terms which has theta 1 dash, those terms that do not have theta 1 dash. So it becomes K1 DC theta 1 dash theta minus K1 DC theta 1 dash plus theta 2 dash plus theta 3 dash into EAC. The next term is K1 DC B1 1 minus theta 1 SS minus theta 2 SS minus theta 3 SS into EAC. The next term is K2 DC theta 1 dash EAC. K2 DC theta 1 dash EAC plus K2 DC B2 theta theta 1 SS EAC K3 DC theta 3 dash. Last term being K3 DC B3 theta 3 SS EAC. Yeah, you get the entire like this. Now, what is the next step? The next step, just give me a moment. K2, B2. Okay. The next step is to find a theta 1 dash, theta 2 dash, theta 3 dash. How do you do that? What is the expression? So you have, let me write in terms of gamma d theta 2 by dt equal to k2 theta 1 minus k3 theta 2. Gamma j omega theta 2 dash EAC equal to k2 dc 1 plus b2 EAC theta 1 SS plus theta 1 dash EAC minus k3 dc 1 plus b3 EAC theta 2 SS plus theta 2 dash EAC. You have such an expression. You can, what you have to do is, you will get two expressions. Same way. So you will have some expression in terms of like x into theta. Okay. From this equation and so on, you will get x1 theta 1 dash plus y1 theta 2 dash equal to something. Okay. Like it will be in terms of some constant. Same way, solve the next mass balance equation. There also you will get something. You have to solve both the equations and find out what is theta 1 dash plus theta 2 dash. Okay. And then we'll be substituting it back into this equation which has been solved till now. And then you have IFEAC. This is actually IFAC. So IFAC by EAC will give you IF. So that's how you will be finding out the entire expression. Okay. So if anyone wants, you can try out this part. And if you have any doubt on that or you're getting stuck, tell me, I'll be solving it. But now, presently, because of the time constraint, I'm leaving it over here. Okay? Is that okay? So, based on this, there are few questions to solve. We'll look into that first. Let me take that now. I think we have to now do 7 to 10 question and assignment 6. Okay. So, let me write down the question. So, yeah, one more thing. Before going into that. So now the question is why you have done like this. So you can look into the journal publications and all. So there is mechanistic analysis of different metal dissolution in different solutions using impedance method. So presently we have stopped with two adsorbed intermediates, but instead of two, you can go with three, four, five adsorbed intermediate also. So in that case, the equations becomes more complex. So simple pen paper solving won't work. You need to have some software like MATLAB or something to code it and then solve it. So once the entire code is done, what we can do is we can give some initial parameter values to values like K1, K2, K3, etc. Then B1, B2, etc. Then gamma value. And then we try to see how the curve is. And then we can use some optimization code and try to fit your experimental data with such a what to say modeling. Okay, so that is prevalent. So if you take, you can find the metal distribution of cobalt. So now it's not multiple at some of the intermediates, not two, but multiple, literally and four. So it's a difference use this for everything like carbon dioxide reduction to format or something. It involves multiple steps. You can use it for it, but that we actually limit to only the baby step, but we can add more like and try to figure experimental mechanism. This magnesium dissolution, iron dissolution, all this. Although we say NCD 72 plus, it might not be happening in a single step, but it will involve multiple steps. So, yeah, in such a case, we can make use of mechanistic modeling. I hope that's clear. So that's the application. We can actually take the impedance data and then try to fit. You propose a mechanism and you try to fit it, and then you can say, okay, this mechanism, the K1, K2 parameters are going to be this much. So to improve the confidence in your fit, what you can do is you can get for example, you have your data something. You'll be taking it at different O potentials. So you, for one of it, you're getting like this, and something like this. Okay. For the next one, you are. I can give an example. You got something like the first one. The next one, you're given different potentials. So when the potential decreases, you are expecting a drop in the second loop. Now the next one. Sorry, I made a mistake. So basically, chart double layer behavior wouldn't change. So if I give it in different colors, the first one, something like this. Now when it is the next one, you are increasing the over potential. So let me say the black one is OCP. Then the next one I'm giving 0.1 volt away from OCP. You can expect something like this. Now for the next one, where I'm going for a zero point 0.2 volt, the double layer behavior wouldn't change, but this one behavior keeps on changing. So yeah, you have multiple curves like this, and then you can predict, you can propose a mechanism. Okay, try to fit the mechanism with what to say the experiments is often experimentally. Okay, so I'm giving an example. So once you fit it, you basically going for some optimization code. You will find out what is the value of K1, K2, K minus 1, K minus 2. You'll also find out the value of B1, B2, B minus 1, B minus 2. Many such parameters involved. Then you'll have also gamma. B1 means actually it is going to be B equal to alpha NF by RT. So by finding B, you are actually finding alpha value. So yeah, then you'll find out the total available sites for the reaction. So you will be once you fit the mechanism, you'll get all these parameters, and then you can say, okay, for this mechanism to happen or such a experimental data, you have to get these are the parameters for the reaction. So when you're trying to give multiple better different potentials, you are giving better confidence to the data you obtain. Yeah, so that's how it is proceeded. Okay, so now let's look into the assignment. Let me just take it. Give me a moment, I'll just take it out. Previously, now the derivation we looked into, but I'll just show again. So you see here there are, but there is a difference. How is it different? Our previous case was like the look M sub gives M sub plus electron. That step is same. The next step is M sub giving M sub 2 plus electron. That is also correct. Third step is a different one. That one, the excitement question is M sub 2 plus gives M sub 2 plus solution. Here M sub 2 plus is M sub M solution 3 plus. Isn't it? So what is the difference in both of them? Here in all the three steps you have electron transfer. Here you have only electron transfer in two steps, which makes this one chemical, this is electrochemical, this is also electrochemical. Why is that important difference? Because here you are finding out IF, and IF corresponds to only those steps where electron transfer is happening. So you have to only consider step 1 and step 2, right? So how do we do it? What is the rate of the first step? This K1. So you see there are two adsorbed intermediates. Which are they? MnSO plus, MnSO2 plus. So here the fraction of site occupied by the metal is K1. That is a rate. What is the fraction of site occupied by the metal? Which is subtracting that by theta 1 and theta 2. So 1 minus theta 1 minus theta 2. What is the reaction rate of the second step? K2 into what is this? Mx of plus. So it is theta 1. Right? Now third step we don't have to consider because it doesn't involve a transfer of. Okay, question 1, 2 and 3 we actually did it in the last class. I mean, okay, I'll just show it to you if you want. Just let me finish this question and then I'll show you. Okay? Yeah. So here IF becomes what? F into rate of reaction 1 plus rate of reaction 2. So all of forward reaction we have to only consider step 1 and step 2. So it is K1 1 minus theta 1 minus theta 2 plus K2 theta 1. So this is the expression we'll get. Okay, let me just complete question number 8 and 9, which is also a continuation of this, and then we'll move on to the first, second, and third question. Okay. So the eighth question says, In the above mechanism, in kinetics limited regime, maximum number of loops that one can expect in complex plane plot is. So if I'm plotting this mechanism, how many loops can I get? So here you have it's so for a Faraday reaction, okay, with a because of Faraday reaction, number of loops maximum expected can be lesser than that if the tau values are constant. They are already RC values are equal or nearby. You can see the loops merge that we have seen previously. Maximum how much we can expect is equal to number of adsorbed intermediate. Here, how many adsorbed intermediates are there? M adsorbed plus and M adsorbed 2 plus. So here you can expect two loops. But wait, this is because of the Faraday reaction, right? But you also have what is the total impedance? How do you calculate? You'll do 1 by ZF plus 1 by due to double layer capacitance. So this one will also add up one loop. So for any reaction, Faraday, because of that, you have only those many loops corresponding to number of intermediate. That's the maximum you can expect. But when you are talking about the total impedance, you have an additional loop because of the double layer capacitance. So here also in this case, how many are there? 2 plus 1 equal to 3. This was question number 9. I skipped question number 8. So let me go to that. So here you will have 3 loops. So question number 8 is direct. I'll just write it down. In above mechanism, how many intermediate species are present? How many species are present? MH of plus and MH of 2 plus. It's a kind of direct question. Just 2. So question 10. So 9 we have already discussed over here. Question 10 I have to discuss a little theory part and then we can go to it. So before that you had asked me question 1, 2, 3. We had discussed in the previous class. Yeah. So the question is, the first one is you have, I'll read out the question. Consider the reaction T is based on electron transfer, electron absorption reaction, EAR mechanism. So you have a reaction T solution giving Q solution plus 1 electron transfer and A solution, it is in the solution, something is getting adsorbed onto the metal surface to form A adsorbed and the electron transfer is involved. Forward reaction K2, backward reaction K minus 2. Kinetic parameters K10 is given, K20, K minus 20, K20 is given, B1, B2, gamma values are also given. So first question is at EDC at a given potential 0.25 volt per CP, what is the surface coverage of A adsorbed? That is what you have to do. So you have to write the mass balance for the adsorbed intermediate. You have to then equate it to 0. That's the first step. So I have written it. This is a step. The first step is not considered. You have to consider the steps where we involve adsorbed intermediate and that is A solution minus it gives A adsorbed plus electron. So how will the the gamma, the mass balance for the step becomes gamma d theta by gamma d theta by dt. There's only one subdeterminant. I'm writing is theta. Forward reaction involves formation of the answer. So it is K2 A solution minus. So we already discussed on the surface of the metal, A adsorbed is getting adsorbed and that occupies theta surface. And there are two competing reaction happening. One, P giving solution, Q solution. So here this will happen only in those fraction of sites which are not occupied by A adsorbed. That is 1 minus theta. Now, is that the only reaction which happens on that surface? No. Which is the other reaction? You have A solution giving A adsorbed. And the backward reaction, A adsorbed giving A solution. So this A solution also progresses only on that step. That is the forward reaction. A solution giving A adsorbed progresses only on that part where A adsorbed is not involved. So that step also involves A solution, no, 1 minus theta. Why? Because that is also progressing in those areas where metal is not covered with air solvent. So, because of that, K2 into A solution, which is the rate of the forward reaction, to 1 minus theta, because the entire surface of metal is not available. Minus backward reaction, K minus 2 into theta. When I'm substituting to 0, theta value becomes theta SS. Rearrange, we are getting something like K2 dc, A solution minus by K2 dc into A solution minus plus K minus 2 dc. Okay. Now, which are the values you need? A solution is 100 millimolar, which is 0.1 molar into 10 to the power minus 3 mole per centimeter cube. Why we are solving it in mole per centimeter cube? Because K10, everything is given in centimeter per second. Now, in this step, you don't know what is K2 dc. How do we find out? At steady state? K2 dc equal to K2 0 exponential. We already know the rate constant is exponentially related to potential. We know what is K20, K10. So K2 dc is K20 exponential of P2 EDC. K20 is given as 10 to the power minus 6. And then you also have D2 value given as 20 volt inverse. EDC is 0.25 volt versus OCP, for which you have to find it out. So when you solve it, you will get K2 DC value. You know K2 DC, you know A solution value, substitute it, find out what is the steady state and fractional coverage. Yeah, you have to also find it K minus 2D, which is K minus 20 exponential B minus 2 EDC. So K minus 20 value is already given in the question as 10 to the power minus 6. B minus 2 is a minus 18 volt inverse. Not forget to put minus 8 minus sign and make that mistake. You have K minus 2. Substitute all this which all. K2 DC A solution, K minus 2 value. Solve it. You will get theta SS value. Okay. So I hope this question is clear to you. You will have to do the mathematics, but before that, first step involves solving the deriving the equation. The next step is finding out the unknown quantities by like K1 DC, K2 DC. You need to know the formula. Find substitute in the derived equation and find the value. Okay. Now the next question was at the same potential, which is 0.25 volt versus OCP. You have to find out the total Faraday current. So the total Faraday current is again dependent upon all the steps where electrochemical reaction is involved. So you have here all the three steps. That is the first step, second step, and the backward step of the second step. All these are having electron transfer. So all of them correspond to current. So you need to have the answer in milliamp per centimeter square. Now, IFDC means you have to make K equal to KDC, theta becomes theta SS. What is the expression for IFDC? You have to consider P giving P solution. So that step has a rate expression of K1 DC, P solution into 1 minus theta SS. Now, forward step of the second step, which is K2 DC, 1 minus theta SS, A solution minus. Backward step is K minus 2 DC theta SS. Because it's backward, we are putting negative sign. K2, K minus 2, we already found out in the previous question, right? Then what you have to find out is P solution, A solution minus. A solution minus we already found out in the previous question. And P solution is also constant, same value. That also you know. Now what else you have to find out? You have to find out K1 DC. What is K1 DC? K1 0 exponential D1 EDC. So K1 value is already 0 is 10 to the power minus 5 and D1 is 10 to the power, sorry, 20 volt inverse. Substitute that, you will get the value of K1 DC. Now, substitute all the value in this. So, you need to know the units. Like, this is coulombs per mole, and all those are in moles per centimeter square, etc. Solve it. Finally, you will get the milliamp per centimeter square value. Okay? This is how you solve in this question. Is this clear? You can probably take a picture or something because you can then solve it and cross check if what you've done is correct or not. Okay, just give me a moment. Yeah. Now let's move on to the third question you told. At the same DC potential, EIS data is required. The amplitude perturbation, at a very small amplitude perturbation, the charge transfer resistances. So, first you have to know what is the YF equation. So, I don't know for your final exam, like if you are given such big equation, rather than by hearting, you may have to know how to derive it because we don't know what is the mechanism. Like I can modify any of the expression like P solution giving Q solution. I can make that reversible and ask that to you. So just learning the values by heart or the derivation by heart wouldn't help. You should know how to solve it. So only when you solve these multiple times, your speed will increase or it will improve. You will be able to solve it first. So yeah. So instead of trying to learning all this by heart, you need to know how to derive it without making a mistake, so that you don't get stuck in any of the steps. So because I can twist and the question can be twisted and turned anyway. Like P solution given Q solution, I can make that do reversible step and half. Then the expression totally changes. So from the derivation of EAR mechanism, last class we had seen this the expression YF equal to F into B1 K1 BC P solution into 1 minus theta SS plus B2 K2 BC A solution minus 1 minus theta SS minus B minus 2 K minus 2 DC theta SS minus of the bracket K1 DC P solution plus K2 DC A solution plus K minus 2 DC theta dash. Okay. Like this derivation I've solved in the last class. You might be getting the link from the Impedance website. I think if you're registered for the course, yeah. So obviously you get the link for the Google Meet. So you should be getting the link for the what is it? For the pre-recorded for the recorded classes. So if you can look at the previous class of mine, you'll see how to derive this. Yeah. So where theta dash value is B2 minus B minus 2 bracket K minus 2 DC theta SS by K2 DC A solution plus K minus 2 DC J omega gamma. This is the expression. Now, you have to find out charge transfer resistance. So first thing you have to understand is when omega tends to infinity, that is at high frequency regime, when whatever value of impedance you get, that is the value of RCT. So when omega tends to infinity, the value of ZF you get, that is RCT. When omega tends to infinity. At this condition, ZF equal to RCT. So you already know YF. Okay. So once you take the reciprocal of YF, you will get the value of ZF. Okay. So when omega tends to infinity, let us see what happens to YF. So all these terms will not be changing except the theta dash. Then theta dash, you come and see this term has a j omega gamma, right? And you're saying omega tends to infinity. So when omega tends to infinity, the entire denominator will tend to infinity. Because omega is tending to infinity, the entire value is becoming very large value. And there's something divided by infinity. So that means 1 by infinity or any value divided by infinity, you can say it is 0, right? So this means that when omega is for this particular expression, not general, but for this expression, theta dash tends to infinity. Sorry, omega tends to infinity means theta dash is tending to 0. So you have a theta dash in this term over here, right? So this term is tending to 0, meaning this full term, right? This is becoming 0. So your YF expression will reduce to F into V1 into K1 DC P solution. Let me see. Yeah, I've written here. Because the entire term made as infinity theta dash tends to 0, that entire term over here will go to 0. And you have YF equal to F into V1 into K1 DC P1 solution 1 minus theta SS plus B2 into K2 DC into A solution minus into 1 minus theta SS minus B minus 2 K minus 2 DC theta S. First substitute all the value and find out what is YF. So you got this and I'm getting something 0.136. I've just rounded it off to 0.14. So up to you, you can keep it 0.136 or 0.14. Because they have given a range for the answers. So probably better not to what to say, uh, like not to round it off, do it as such. Because otherwise, if you're rounding it off to higher value or a lower value, when you're taking the reciprocal, the value might not come in the range. So be careful. Because when you're solving it, you don't know which range the value they have given us right answer. That's why I'm saying. Now you found out YF to be 0.14. Now how do you find out ZF? ZF is inverse of YF. So you get 7.14. So when omega tends to infinity, ZF value, whatever it is, it corresponds to R secant. Then you're getting it as 7.14. Now the same question at the same DC potential. It's question number 4. At the same DC potential, EIS data is acquired using a small perturbation, and you're supposed to find out what is polarization essence. So when do you say that? Well, how do you find out RP value? RP value is the Faraday impedance when omega tends to 0. So you need to have omega tends to 0 to find out ZF. Or ZF is nothing but 1 by YF. So 1 by YF when omega tends to 0. So go to the YF equation and give omega tends to 0. So here you come again. Where is omega here? When omega tends to 0, what will happen? This term, j omega gamma, will tend to 0 when omega tends to 0, right? But the rest remains, that is b2 minus b minus 2, k minus 2 dc, theta ss by k2 dc into a solution plus k minus 2 dc. So this equation will solve and find out theta dash. Then substitute value of theta dash over here in YF equation, solve it. So it is a little more intense calculation. Then, so as said, theta dash, find it out by substituting omega equal to 0. So that last term will go that 1 by many terms plus j omega gamma. This will tend to 0. Rest remains. You find out theta dash, substitute it in YF equation, find out what is YF. Then ZF becomes 1 by YF. That value will give the RP. Once it's solved, the value will be coming between 100 and 90 ohm centimeter square. You will try solving it. If you're not getting the answer, let me know. Then I'll do calculation. But the methodology remains the same. we already know what is K1 DC, K2 DC, B1, B minus 2, B2, everything from the previous experiment. So it all that you have to be careful because when you're substituting it, you shouldn't make problems with the signs and all. So you will get the value between 100 and 90, negative 100 and negative 90. Okay. So in that again, when the next question was what will be the you're given an impedance spectra, you have a DC potential, and you needed to know what will be the RP value expected to be at 0.7 volt. So we know impedance, we are taking differential impedance. So zero point 0.7 volt is something less than 1 volt. So in this region, you see that this region impedance is reducing. I mean current reduces with applied potential. So when you're taking the differential impedance, you are expecting the RP value to be negative because it is a negative slope. Similarly, in 1.2 volt, it is something like this. This is 1 and 1.2 volt comes somewhere here. You know it is a positive slope for I versus V. So positive slope, this means value will be positive. Yeah, we stopped it over here. That's why we in this class I discussed about 7, 8 and 9 question. Is this clear till this? So yeah, if you have any doubt, you can let me know. So before moving on to the next question, before moving on, because in the above mechanism, at how many DC potential should the impedance spectra be taken so that the kinetic parameters can be estimated with some confidence? So to understand that, we have to look into some theory portion and then we will move on. So we see that. Okay, so this comes under a topic called reaction mechanism analysis. Which is RMA versus equivalent electric circuit. Just EEs. Now, let me take an example. M giving M absorb plus electron, and you have K1. Now, this M absorb plus becomes M solution 2 plus electron. Okay. So, how many kinetic parameters are involved in this? So, what are the kinetic parameters? So, this was what I was talking about the mechanism. Yeah, this mechanism. You will fit, you need to find K1, K2, K minus 1, K minus 2, B1, B2, B minus 2, gamma. These are the kinetic parameters. So in this step, you have K1 associated B1, K2 associated B2, and the total fractional sites because you have elements of this. Now, we have already seen this mechanism, okay? And this mechanism can be fitted using some circuit like this. Okay, So why this? So in this case, you see, so I'm talking only about the Faraday impedance. That is, uh, wait a minute. I have a solution resistance. I have a double layer capacitance. I have then one adsorbed intermediate, which I'm going to model using either an inductor or a capacitor, as per my choice. Okay, I have this much. This is ZF. So these are the kinetic parameters that I'm using to model ZF. For this part of ZF, how many equivalent electric circuit elements do I need to model this? There are two resistors and one inductor. Totally three. So if you see, I am if I'm using an equivalent electric circuit, I need three electric elements versus five kinetic parameters to model the same thing. So why this important? So I already told what do we do in impedance? Impedance when we are modeling it, first we'll try to fit it to a circuit using Z7 software something, we get the parameters. Okay, we get an equivalent electric circuit. Now we're trying to model it using a model we're proposing, where it will have five kinetic parameters. Here you have three electric elements and five kinetic parameters. Now consider a case. Okay, so once again I'm writing. For same model, I'm using three electric parameters and five kinetic parameters. So I'm having five parameters. That means these five parameters are not known. I'm going to model it. I'm going to fit it and find out these five parameters, right? So five parameters are getting mapped to three electric parameters, which we already know, right? This I can add to parameters. We can find out using the Z7 software or something. So 5 to 3, these are unknown. So when I'm having only three values, for example, I have three equations. If I have two equations and only one variable, I can get an infinite solution, right? So same thing happens here. I can go for, if this is the case, I can go for infinite combination. So I won't have any confidence in the data I have obtained. But now if I expect, now I'm telling, if I am taking data at 2 DC potential. Like here, what happens? This portion, this due to ZF, this keeps on changing. But whatever DC potential I'm saying, when I'm modeling it and when I'm trying to fit it, the model parameter shouldn't change. It should be this model, and I'm getting this expression. This should be valid at any applied potential, and at any applied DC potential. That's how unique the model parameter should be, right? That's how you do modeling. You cannot be like, for this condition, there's a model parameter. You change the model parameter, the condition is. Then there's no point in doing the modeling. So if I'm going for 2 DC potential, I'll still have 5 kinetic parameter. But how many electric parameters will I have? This 3 corresponds to 1 DC potential. So what does electric parameter means? So I have a circuit like this. So if I say this one, let me take the example of first the black one. I have something like this. When I try to fit it in ZSM software, it will give me some set of values for C1 or R1, etc. Now the next one, this circuit is same, this one becomes smaller. So will the ZSM software give me the same value? No, your RP value is changing, your RT value is changing. So this will give me another set of CV2 R2 etc. So for each DC potential, you're individually trying to fit it in ZSMN. So you're going to get different set of parameters. So same thing applies here. Again, 3 electric parameter for second DC. So this means totally you have 6 electric parameter. So so that means for n number of DC potential, your what to say, your for any parameter, like for this case, okay, you will still have 5 kinetic parameter, and you will have how many? 3 for one, so 3 and electric parameter for this case. So your kinetic parameters should be lesser than the electric parameter. Only then for all the conditions it will be able to fix it. That is what makes sense. Else you will have an infinite number of solutions. So always DC potential should be such that kinetic parameters should be less than or equal to equivalent electric circuit elements. This is what it means. Now, how do I find it out? Like from either you can for this one. This is the mechanism. You have three-step mechanism where you have what are the things involved. Like you have K1, you have K2. For multi-step equation and all, it becomes difficult to, just do a calculation, internally and say, okay, these many, it becomes difficult. So how do we do that? Okay. So for that, there is a formula. So you have to first say, let me write in the next page. Number of electrochemical step equal to P. You have multi-step, you have to first identify how many number of steps are electrochemical step. Now the next step, find out number of chemical step. I'm saying it is Q number of chemical step. So in that case, number of kinetic parameter will be 2P plus Q plus, don't forget gamma. Gamma stays out. Gamma is like if you have adsorbed intermediate, you will have the fraction sign. So you need to know. This will stay out. So this you shouldn't forget. There's always number of kinetic parameters is 2P plus Q plus gamma. Why 2P? Because in the kinetic parameter step, you have what are the kinetic parameters? K, K1, K2, K3, etc. B1, B2, B3, etc. And you have gamma. So gamma stays out. So that's why you're writing gamma. Right? Now, for a electrochemical step, we know you have rate constant can be expressed in terms of K10, B1, exponential B1E. So for electrochemical step, you will have both Ki and K1 and B1. Okay. So that's why you are writing for any electrochemical step, you will have 2 into P. For every electrochemical step, you will have both B and K. What about the chemical step? In chemical step means there's no electron transfer happening. We'll say that the rate constant is a constant, right? It is not dependent upon the potential. So that is why in that step we'll have only Ki value. That's why we are writing 2P in plus Q, only one, plus gamma. So we get the number of kinetic parameters. Now the next step is find out number of intermediate. If I say that is N. Okay. Now number of intermediates is this much. So number of electric element to represent Zn equal to 2n plus 1. Why 2n plus 1? Because for every adsorbed intermediate, we are representing in terms of one resistor and one capacitor in series. Okay, or one resistor and one inductor in series or something like that. Now plus 1 by 1 comes because when you're drawing the entire circuit, you will have something of this form. This resistor also becomes a part of this one. Or if you're going for a not white circuit. White circuit is difficult to find out like which one corresponds to double high capacitance, which one is for the adsorbed intermediate. So we are not talking about white circuit, but about Maxwell or ladder. Even in ladder, like this, right? For single adsorb. So this entire thing becomes part of ZF. This entire thing becomes a part of ZF. So for each adsorbed intermediate, you have a one RC in parallel or one RC in series. Along with that, you will have one additional resistor. That one comes with 1. So it is 2n plus 1. So we already told the number of electric elements should be greater than the number of kinetic parameters. So finally, number of DC potential required is equal to round off of 2p plus q plus 1 by 2n plus 1. We are always rounding up, not rounding down because that will give a lower value. So you have to always round up. Okay. So this is how you will find out how many DC potential you need. So let's go to the question. I hope this is clear. Now the question is, in the above mechanism, let me write down the mechanism. M gives M adsorb plus electron. K1 M adsorb plus gives M adsorb 2 plus electron. K2 M adsorbed 2 plus gives M solution 2 plus K3. In the mechanism, this question 10. In above mechanism, at how many DC potential should impedance spectra be taken so that kinetic parameters can be estimated with some confidence. So let us follow what we have now done. So how many electrochemical steps are there? Just speak. You have first step is electrochemical, the next step is also electrochemical. So it is 2. So the next is number of chemical step, Q. This is chemical step because there is no electron transfer involved. 1. Now, so what is the number of kinetic parameter? 2p plus q plus gamma. So it's just 2 into 2 plus 1, 2 to the 4, 5, 6. So this is the number of kinetic parameters, right? Now, how many number of intermediates are involved? M adsorb plus, M adsorb 2 plus. M adsorb 2 plus solution. This is going into a solution which is not an adsorbed intermediate. Be careful with that. This M adsorb plus and M adsorb 2 plus. You have two intermediate. So, number of electric component to represent ZF equal to 2n plus 1, which is 2 into 2 plus 1 equal to 5, right? So now you have to find out the number of DC potential required to acquire ES. You have to round up which one? 2p plus q plus gamma by 2n plus 1. So which is round up 6 by 5. So when you're rounding it to 1 point something, when I'm rounding it up, it becomes 2. So 2 is the answer for this question, right? That answer here? Yes. So yeah, in this step, in this class, we actually looked into assignment 6. So where we also, again, we looked into EEAR mechanism. We also saw the three-step mechanism where you have two adsorbed intermediate involved. Then we saw the confidence in DC potential. We need to have, in order to have the confidence in the proposed mechanism, we need to collect data in multiple DC potential so that we are able to map the your mechanism parameters to the DC, to the electric components with more confidence. So yeah, that is what we looked into in this class. So probably in the next class, we will be now moving on to the catalytic mechanism and Franken isotope. Okay. And then after that, few problems. Okay. Few problems that we have actually left out from the previous class, I think. Not from this assignment. I have left out few of them around like how to find RP and RP. So yeah. We'll look into few more problems. Yeah. So that's all for today. We'll now meet in the next class. Thank you. I hope you are able to follow what you had seen in this class. Anyway, thanks for joining. Thank you.